Yeah, hello. I'm very happy to be here. I'm Robert. Today I'll be talking about learning shallow quantum circuits. This is a joint work with Yun Liu, Michael Broughton, Isaac Kim, Anurag Anshu, Zeph Landau, and Jerry McLean. So for those of you who don't know, shallow quantum circuits are essentially just quantum circuits with constant depths. For example, in this figure here, we draw a one-dimensional shallow quantum circuit with a depth of 3. So because of the limited depths, these shallow quantum circuits, they're quite simple in conceptually. However, due to a plethora of prior work, people have established a very good understanding, and surprisingly, despite their simplicity, they're actually quite powerful computationally. For example, in one of our previous work by oh, what? Okay, let's see. Okay. So for example, in this very famous work published in Science in 2018 called Quantum Advantage with Shallow Circuits, it was proven that shallow quantum circuits are unconditionally more powerful than shallow classical circuits. In particular, in this work, they prove a separation between these two complexity classes known as QNC0 and NC0. So QNC0 is just an abbreviation for the set of problems that can be solved by shallow quantum circuits, while NC0 is the classical counterparts. So in this work, it was proven that there is a relational task that can be solved efficiently by a shallow 2D quantum circuit, but no shallow classical circuits of arbitrary size would be able to solve that problem. And in a following work to this example, to this work, published in Stock 2019, it was proven that there's also a separation between QNC0 and AC0. So AC0 are essentially circuits that are slightly stronger than NC0. They are shallow classical circuits that have unbounded fan-in gates. So normal shallow classical circuits just have these Boolean gates that acts on a constant number of bits. But in AC0, they have this unbounded fan-in AND gate, so they're more powerful. That can take an arbitrary number of inputs. And yet, it was proven, actually, this is also a paper in QIP, that there exists a task that QNC0, that is shallow quantum circuits, can solve efficiently, but it requires an exponentially large AC0 circuit to solve. And furthermore, if we make some standard complexity theoretic conjecture, then it was also well known that, say, for example, assuming polynomial hierarchy doesn't collapse, then shallow quantum circuits are hard to simulate classically. In particular, there are some sampling tasks. One could set up the shallow quantum circuit in some way, and based on ideas from measurement-based quantum computation, one can show that sampling from shallow quantum circuits are classically hard because it can generate distributions that are highly non-local. Given these computational power of shallow quantum circuit, it raises this hope that perhaps maybe these shallow quantum circuit can be used as machine learning models in some task that might have some quantum advantage. However, despite this hope, or I should say, because of this hope, there have been a plethora of prior works. There's maybe thousands of papers that have been written about training and learning parameterized shallow quantum circuits. And in the literature, it's also known as shallow quantum neural networks, where the idea is pretty simple. We just parameterize all the gates in the quantum circuit, and we try to use like standard optimization algorithms like gradient descent or Newton methods to try to train them to minimize loss function and hope for the best. However, despite a lot of these interests, up until this point, there's no efficient learning algorithm that was known for, for learning shallow quantum circuits. So for today's talk, what I would like to do is I would present some of the challenges that people have faced in learning shallow quantum circuit. Then I would talk about some of our new ideas for addressing these challenges and end with some potential applications. Let me begin by first talking about the challenges that people are facing. So the first challenge is more foundational. So for people that are familiar with classical learning theory, there's these very foundational results from 1990 that essentially prove that shallow classical circuits are computationally very easy to learn. In particular, it was proven that for the standard shallow classical circuit, NC0, it can be learned in polynomial time using essentially junta learning techniques. Because due to the structure of shallow classical circuit, it would have kind of bounded causality, and then the relevant variables is very few. So we just need to be able to learn like these kind of low degree-ish functions. On the other hand, there's also another strengthened result on learning AC0. It was proven that AC0 can be learned in quasi-polynomial time using ideas from Fourier analysis. And that essentially opens up this field called Boolean function analysis. While there have been these foundational results for learning shallow classical circuits, they often requires like ideas from low degrees from sort of junta um, situation, which are not which are not present for learning shallow quantum circuit, because as we have discussed, shallow quantum circuit can generate classical distributions that are classically hard to sample from and are highly non-local. And hence, the existing techniques that one would use to learn NC0 and AC0 classical circuits doesn't apply for learning shallow quantum circuit. Another more bigger challenge that have been faced in the community is considers optimization landscape. So while shallow quantum circuits do not have barren plateaus in various cases, it was well known from both numerically and experimentally and also theoretically that their landscapes are swamped with exponentially many bad local minimum. For example, this is a figure from a paper by Bobak and Eric published in Nature Communication 2022, where they essentially prove and also numerically showcase that we can see the landscape looks very bad, even just like some 2D slice is already looking very bad. So as a result, when we just start from some point and try to do standard optimization like gradient descent and Newton method, it can easily get stuck into some bad local minimum and fail to escape. Even if you try to forcefully push the point out, it would just get stuck into another local minimum. And hence, the standard methods for training like variational quantum circuits often don't scale to bigger system sizes. And this challenges really raise this question, which is, are shallow quantum circuits computationally hard to learn? And if the answer to this question is yes, then it really kind of doomed this field of trying to use parameterized shallow quantum circuit to do anything useful, for example, optimization and learning, etc. So in the following, I would like to shed some positive light on this aspect. There have been a lot of very interesting results that showcase the negative part of this. Like for example, if we consider certain restricted model, then learning distribution generated by shallow quantum circuits are very hard, for example. So yeah, so I would then go into presenting our provably efficient learning algorithm that allows one to learn arbitrary shallow quantum circuits. So let's say we consider there's a ground truth unitary that we would like to learn about. So this is a unitary U that's over n qubits generated by a shallow quantum circuit. And let's say we wanted to learn this unitary in the sense that we want it to have certain behavior. Like in classical learning theory, we often have like a sample of data that says, for this input, I want this output. And for that input, I want that output. And how can we learn a circuit that produces this? Here, it's a similar setting. For example, we want the unitary U, given certain inputs, would generate some classically hard distribution. And given some other input, it would generate a different classically hard distribution. Or for example, from a more like a quantum dynamics perspective, we wanted to learn some unitary such that given an input state, it would produce the correct output state. So the question is, how can we learn this unitary U efficiently from some data set? The standard approach that people often do is is based on this parameterized quantum circuit. We just parameterize all the gates in the circuit by some real vector. And what we were going to do is we're often just going to guess some initial point, and we're going to check the loss function to see if the guessed circuit behaves accurately as sort of the ground truth circuit. If it doesn't behave accurately, we try to update the parameter using gradient descent, etc., and repeat step 2. So just run check and then update, check and update, and so on. However, as we have discussed, this exponentially large search space contains exponentially many bad local minimum. And hence, this standard strategy that was often used in classical machine learning doesn't really quite apply for this situation because the landscape was so rigged and it would just easily get stuck into some of these traps. So the proposed strategy in our work is to consider a very unconventional parameterization of a unitary U. So instead of looking at parameterized quantum circuit based on these parameterized gates, we're going to define a notion called local inversions and then utilize local inversions to parameterize the circuit. And then what we're going to do is we're going to learn or train these local inversion to minimize the loss function. So in order to dive into this proposed strategy, I would first like to define what we mean by local inversions. So suppose we have this n-qubit unitary U. A local inversion Vi, or Vi is the local inversion of U on qubit I if the following relation holds. That is, if we compose U and Vi, just another unitary, UVI, we want UVI to act approximately as identity on qubit I. But more formally, what we want is that we want the left-hand side, so that is, there are some channel acting on n-1 qubits, tensor product with an identity on qubit I. This would be approximately equal to UVI under our favorite distance metric. It could be, say, the diamond distance, or it could be the average case distance, like average gate fidelity, etc., or some other distance. And more precisely, we consider the channel acting on the n-1 qubits to essentially be the reduced channel of UVI. That is, we look at UVI, and for the ith qubit, we just put in a maximum mixed state, and then we trace out the ith qubit. So you want this left-hand side object to be approximately equal to UVI. And that's what we mean by VI being a local inversion. But on a very high level, it just really means that when we compose U and VI, qubit I will be acting as identity. It would add X identity on qubit I. So we can stay here for a bit and let's say think of U as being a shallow quantum circuit. So if U is a shallow quantum circuit, then its local inversion are actually quite simple because of the bounded light cone in shallow quantum circuit. All these local inversions only need to act on a constant number of qubits. And hence the training can be done in this much smaller space. So now, suppose we are given the local inversions for each qubit. So we have a big unitary U, and for each qubit, we have these local inversion, which acts on only a few qubits. How does these local inversion parameterize the big unitary U? Or does it even uniquely specify one? For example, if we think of it in terms of states, if we have a quantum state with n qubits, and we look at, say, the reduced density matrices, that doesn't parameterize the state because it lacks a lot of information. So one could ask the same thing. If we have local inversions for every qubit, does it really parameterize an n qubit unitary U? So in order to show that, what we are going to give here is a universal procedure that allows one to sew together these local inversions to form the original unitary U. So here one should think of U as being unknown. We don't know what U is. All we get are these local inversions, V1 to Vn. And what we wanted to do is to use these local inversions to create the unitary U. In particular, what we're going to do is we're going to write down a circuit that essentially implement U onto psi. And the idea is as follows. So in the initial step, we will prepare two n qubits. N of them are in maximum mixed state, while the other n is in some arbitrary pure state psi. And because the n qubits are in maximum mixed state, we can use our imagination and imagine that the ground truth unitary U is just applied onto this maximum mixed state. And the reason we can imagine that is because no matter what unitary was applied onto the maximum mixed state, it's still the maximum mixed state. So we can just kind of use our imagination to have this imaginary U that was sitting there. And now the procedure looks like the following. First, we will use the first local inversion, V1, to apply it onto the state, which, because of the definition of local inversion, it would open up a hole that allows us to kind of peek into the first qubit. So it uncovers the first qubit. And what we're going to do then is we're going to throw away the first qubit, which is going to trace it out. So now we're left with one less qubits. And however, there's this weird n-qubit, n-1 qubit channel that was applied to the n-1 qubits. What we're going to do then is we're going to rewire the first qubit of psi and put it into that empty hole, and then implement the inverse of the local inversion. So that's kind of recap what have been happening on the operation side. If we disregard the state part, then all we're doing is we have this imaginary U, and then we implement V1, and then we implement V1 dagger. And hence V1 and V1 dagger would just cancel it out, and we would just get a U back. And hence, the whole procedure looks like following. We have this imaginary U that kind of sits on top of these maximally mixed state. Think of them as like trash. Using these local inversion, we can open up punch holes into them, and then we can just pick those trash out. And then we use the inverse of local inversion to heal it back, and now we have U. But the one thing that's changed is now the first qubit of psi is being applied into U. And then we can run these 6 steps again and again in arbitrary order. We can do it with like first qubit, third qubit, sixth qubit. We can run it in arbitrary order and gradually just throw away all these maximally mixed state, and then at the end we will have this ground truth U being applied onto the n-qubit state psi. And hence, initially we have these local inversion, but we don't know what the U is. Using this procedure, we will be able to sew together these local inversion in order to form the n-qubit unitary U. And now using this technique, we are able to prove the following theorem, which states that any n-qubit shallow quantum circuit U can be learned to a small diamond distance in polynomial time. So note that diamond distance is the worst case distance that considers all possible input states as well as all possible observables that we measure after it. And we will be able to learn a good representation under diamond distance for an n-qubit circuit. And furthermore, the unknown circuit, the ground truth circuit U, can really be of any connectivity. So it can have highly non-local connection, and still we can learn them very efficiently. On the other hand, if we do know what the connectivity is, kind of like in many setup for a parameterized quantum circuit, then in those cases, the computational time can be very efficient and it will be roughly like n-cube instead of some large polynomial. Using the similar ideas based on local inversion, we can also prove a related theorem, which instead of learning circuits, it's about learning states. So we can show that any state rho that's prepared by a shallow quantum circuit, but here there's an additional restriction, which is it only applies to at most 2 dimension. It can be learned to epsilon trace distance in polynomial time. And also one thing I forgot to mention is that here in this theorem, the algorithm only requires having a classical data set that describes the desired behavior. That is, for some random product state input, and the measurement outcome is this. We want to match that, which is very similar to like the classical learning theory results about learning shallow classical circuit. We have some samples of inputs, and we wanted to learn to predict what the output is. And here we can do that in a similar fashion. So it only requires a classical data set. It doesn't require any quantum data. And for theorem 2 as well, we only require some classical data set that have the randomized Pauli measurement on the state rho. So with these provably efficient learning algorithm that allows one to learn any shallow quantum circuit, we can ask, what can we do with them? What are some potential applications for for using this algorithm. So I should note that a lot of these applications I talked about has already been proposed in the community because people have been studying shallow quantum neural networks for a long time, and there are multiple various different applications that have been proposed, even though there's no efficient learning algorithm. But now with the efficient learning algorithm, we can a lot of them would just come through immediately. So the first application is relatively straightforward. It's that we can learn quantum dynamics. Suppose in nature or in the lab, there's some unitary that we would like to understand better to learn it. And suppose that that unitary is generated by a constant time dynamics. It can be any constant, um, or it can be generated by or approximated by shallow quantum circuit. Then using this learning algorithm, we will be able to efficiently learn these quantum dynamics and be able to predict what happens for other states, for any other states. Another application is actually not related to learning at all. There's no learning in here, but it can still be used. So the idea, the task here is in compressing circuit. So suppose we have some n-qubit quantum circuit that we would like to implement in the lab. Here we know everything about that circuit. It was given to us, so there's no unknown. However, what we would like to do is we would like to find a shallowest circuit, like try to find a constant depth circuit that approximates it and implements that same unitary. So in order to apply it to this task, the idea is to think of that the shallowest circuit for implementing that unitary as an unknown shallow circuit, and then apply this learning algorithm for learning shallow circuit to discover what that shallow circuit is. And there are various other examples that people in the community has came up with, such as in speeding up Hamiltonian simulation, in learning classical distribution that are hard to classically sample from, but quantum computer can sample very easily, etc. So all of that could just all fall under the umbrella. So those are some applications. And now to conclude, in this work, we proved that shallow quantum circuits, any shallow quantum circuits, are efficiently learnable, even though they are classically hard to simulate. And hence, it provides this very nice and natural class of quantum circuits that have quantum advantages, and yet we can efficiently learn them. So despite these progress, there's still a lot of interesting open questions that I would love people to solve. For example, what about learning certain deep quantum circuit? We know that for in the worst case, there are deep circuit that are very hard to learn, but perhaps by combining this technique with some new ideas, such as maybe sums of square, for example, we might be able to learn certain deep quantum circuit. That will be very interesting. Or how can we learn high dimensional states? Like the theorem 2 that I presented, it only works until 2 dimension. How can we efficiently learn 3-dimensional states or higher dimensional states or states with arbitrary geometry? And these are all very interesting questions. And for people that are interested in the details of this work, the paper just came out an hour ago, so feel free to check it out. And that's it for my talk. Thank you so much for listening.
Okay, we have time for questions. If you have a question, I would ask that you please go to the microphones in the center of the aisle.
Nice talk. Thank you. Can you comment on your maybe anything technical you can say or your intuition around what happens when your unitary circuits are maybe approximately unitary, so that maybe they're noisy or something like this?
You mean like what if the circuits we would like to learn is actually some channel?
Yes.
So if it's a highly like it's very far from the unitary kind of boundary, then at the moment I would say that's also an open question. We did thought about it, but it doesn't seem very trivial to extend. However, if it's close to the unitary, I think using this protocol, essentially what happens is it would push to the closest unitary. So
Yeah, okay.
yeah.
Hi, thanks for the nice talk. So, how does your algorithm perform in learning non-shallow circles like log depth?
So if the circuit is geometrically local, like let's say it's in 1D, 2D, or 3D, etc., like these kind of finite dimensional circuit, it can learn log depth circuits efficiently. However, we also have a result in the paper that says if you wanted to learn up to a small diamond distance, a log depth, highly non-local circuit, then the query complexity has to be exponentially large. So there are worst case instances for learning log depth circuit.
All right. Okay.
Yeah.
Thank you.
No problem.
Thanks for the nice talk. I mean, you might have partially answered my question, but can you, so from your protocol and technique, it seems like this local inversion and sewing technique, it seems very general. So can you give some intuition that why the shallowness is important, why this fails for deep quantum circuits?
Yeah. So I don't think it fell. It's just kind of the cleanest theorem that we can write down at the moment is for shallow circuit. And the reason is because for shallow circuit, doing local inversion, like finding local inversions and learning them is or training them is very easy because in shallow circuit, every the light cone doesn't spread to too many things. So then if you just consider few body unitary, they will form local inversion, and hence we can train them efficiently. However, I do believe, like, for example, that's kind of the hope for this open question, which is suppose there are some structure in the deep circuit, then perhaps we will still be able to learn or train the local inversions efficiently. And then in those cases, we will be able to learn them.
Would it be related to expressibility of these like unitaries or?
Definitely expressibility would come into play. I think but at the same time, I don't think yeah, it's not yet clear to me. Of course, low expressibility deep circuit, I think they will be efficiently learnable. However, I also feel like there should be some like more expressive deep circuit that are still learnable. So.
Thank you.
So thanks for the talk. I just want to clarify the technical step where you pick up the garbage and rewire the actual state. So there, you claim that this V dagger and V will cancel each other. But I wonder because in between them, you sort of trace out the original qubit and rewire in another one. How does the V and V dagger cancel?
Yeah, that's a great question. So indeed, in here you can see that we start out with U, and then we apply this V1. It becomes like this, and then we did do this disposal operation. But the thing really is coming from local inversion because when V1 is the local inversion, then the first qubit will just get uncovered, right? Like now there's no operation acting on it, and hence when we play with the first qubit, like kind of do this tracing out and then rewiring from the upper part, like if you just kind of hide the lower part, nothing really happened, and that's why one can this V1 dagger and V1 will cancel it out. So that's intuitively what happens, but mathematically one can kind of just write out the whole procedure, and one will see that as well.
Okay.
Hey, thanks for the lovely talk. Looking at the procedure, I was vaguely reminded of this fact we know of QNC0 circuits that on a fixed input, there's a commuting local Hamiltonian that whose ground state is the output of that thing, and then the actual state is equal to the product of the projectors.
Yes.
Is there some formal relationship to this that you know?
Yeah, that's also how like we got involved. Like we were talking to Anurag about this and talking about ground states. Like how can we learn ground states and then this shallow quantum circuit kind of give a nice picture to it. So indeed, there is a parent Hamiltonian such that the ground state, like a commuting parent Hamiltonian, where the ground state is the state prepared by a shallow quantum circuit. However, there's a lot of challenges. For example, in 2D, we don't know how to efficiently find ground state. So that kind of also is another challenge that we were originally facing about learning these states generated by shallow quantum circuit, because we don't really know how to find ground states of commuting Hamiltonians in 2D or higher efficiently. And hence the learning is not efficient. It is sample efficient, but not computationally efficient.
Thanks.
If there are other questions, we'll take them into lunch. And let's thank Robert and both speakers again.